Hello student, in this video I am going to discuss about JPEG algorithm, which is widely used in case of photo compression technique or image compression technique, which is developed in the early 90s, or you can say late 1980s. They developed this a joint photographic expert group developed this new algorithm to address the problems of that era, specifically the fact that consumer level computers had enough processing power to manipulate and display full color photographs, but however full color photographs required a tremendous amount of bandwidth when transferred over the network connection. That is why they try to understand how an algorithm or how a technique can be created where low amount of data will be compressed without losing many or more data. Means it's a process of compressing the main image file with high ratio and losing the data in minimal way. So that is the idea about JPEG, purpose of this JPEG. And due to the nature of this compression algorithm, JPEG is excellent at compressing full color photographs. That is, maximum is 24 bit, means 8 bit per three colors is RGB. Red is 8, Z is 8, B blue is 8, so 8 into 3, 24 bit. So that is the maximum file size can be, and that type of file can also be compressed using JPEG, or compressing grayscale photos that include many different shades of gray. Not only JPEG is applied on color photographs, it can be applied on grayscale, because in different type of grayscale images also there might be lots of levels of shading of black and white. So in that way, or in that type of scenario also, JPEG can be very helpful. JPEG algorithm does not work well with web graphics, line art, scan text, or other images with sharp transition at the edges of the objects. So try to understand the drawback of this JPEG algorithm, which does not work that much good or that much well with a web graphics, or we can say line art or scanned text or other images with sharp. Means if the edges of those objects are sharp, or there are transitions at the edges of those objects which are sharp enough, in that kind of scenario the working of JPEG it might not be fruitful. The reason is this is so will become clear in the following sections. So we'll try to go through the techniques of JPEG one by one, how much we can go. Please try to be focused in this document. I'll share this over Google Classroom also, and it is very important to understand how we can compress in photo. Basically, JPEG compression and decompression consists of four distinct and independent phases. First, the image is divided into 8 pixel blocks. Next, a discrete cosine transform is applied to each block, convert the information from the spatial domain to the frequency domain. So try to understand this. Actually, initially, the data we have was in the form of information or bits, but which is converted to frequency domain by using discrete cosine transform. After that, that frequency information is quantized to remove unnecessary information, and finally standard compression techniques compress the final bit stream. This report will analyze the compression of grayscale images and will then extend the analysis to decompression and to color images. So here we'll try to go through an example of grayscale only, but that can be maximized or extend to color image also. So here you can see the four distinct level or independent phases, and we are actually discussing about how we can convert, or how we are manipulating the actual information in frequency domain actually, and that is why it is making it more stronger one in case of other compressing techniques. So this is a basic diagram. Okay, basic diagram of the process. We'll try to go through it. Okay. Phase 1. In the phase 1, it divides the image. Attempting to compress an entire image would not yield optimal results. So it says that if you go to the entire image, would not yield optimal result. Therefore, JPEG divides the image into matrices of 8 by 8 pixel blocks. This allows the algorithm to take advantage of the fact that similar colors tend to appear together in small parts of an image. Obviously, if you go through any kind of image, having similar color will be over a specific block or a specific area of the picture or the image. There might be, suppose if you say some green ball, so in a specific block or in a specific area of the image only, that green color will be there in that image. So that idea, that notion is used here, because that is why this algorithm take the advantage of the fact that similar colors tend to appear together in small parts of an image. So that is why divided into 8 by 8 pixel blocks. So blocks begin at the upper left part of the image. And are created going towards the lower right. If the image dimensions are not multiple of 8, extra pixels are added to the bottom and right part of the image to pad it and to next to multiple of 8, so that we create only full blocks. To try to understand this, we try to pad the matrices to create complete 8 by 8 pixel blocks. If the original image does not have multiplication of 8 by 8 blocks in information or data or bits, then it will add up by adding some null value or dumb value or dummy value. So that dummy values are easily removed during the disk decompression. So we don't need to worry about those dummy values which are created or included in the picture just to create 8 by 8 pixel blocks. From this point on, each block of 64 pixels, because 8 by 8 is equal to 64 pixel. So 8 by 8 or 64 pixels is processed separately from the others, except during a small part of the final cell compression step. So each block of 64 pixels is processed separately from the others. Now, after dividing in 8 by 8 or 64 pixel block, each block will be processed separately from the others, except during a small part of the final compression step. But at the final step or the final compression step, all together might work, and that will be discussed how. But entirely in the whole episode of this algorithm, those 64 pixels are processed separately. Phase 1, in case of phase 1, divide the image, optionally include a change in color space. Normally 8 bits are used to represent 1 pixel. We know that in case of red, it will be 8 pixel. 8 bits are used to represent 1 pixel. Each byte in grayscale. So if we are talking about grayscale, then may have the value 0, fully black, 255, that is 2 to the power 8 is equal to 256, and we are starting from 0, that is a 0 to 255. So 0 to 255, 0 is fully black and 255 is fully white for grayscale image. For color images have 3 bytes per pixel, so 1 for each component, red, green, blue. However, some operations are less complex if you convert these RGB values to a different color representation. Normally, JPEG will convert RGB color space to YCBCR color space, and that is very important or hidden point you might not understand, or you might not have seen anywhere before, that RGB is initially converted to YCBCR color space or color model before actually going for the division of the image. So that is the step. Here again, in YCBCR, Y is the luminance, which represent the intensity of the color. CB and CR are chrominance values, and they actually describe the color itself. So YCBCR tends to compress more tightly than RGB, and any color space conversion can be done in linear time. The color space conversion may be done before we break the image into blocks. So before going for the blocking or dividing the whole image, we can convert the RGB to other model, or any conversion between different model can be done, and it is up to the implementation of the algorithm. So that can be different for different perspective of the algorithm, but that is advisable because this is easier to do in case of YCBCR, and which is more good and tightly we can compress more tightly in case of YCBCR rather than going for RGB. So finally, the algorithm subtract 128 from each byte in 64-byte block. Here we have divided this grayscale image, which have 0 to 25 to the values, random values between these two values, where 8 bits are there. So we are subtracting each pixel or every value of the pixel 128. The algorithm subtract 128 from each byte in the 64-byte block. 64-byte means 64 pixels block. This changes the scale of the byte value from 0 to 25 to minus 128 to 127. Obviously 0 minus 128 will be minus 128, and 255 minus 128 will be 127. Thus the average value over a large set of pixels will tend towards 0. So initially the average value of 0 to 255 will be close enough to 127. So but after doing that, we are closing that value towards 0 or 10 towards 0. The following images shows an example image. That image divided into 8 by 8 matrix of pixel blocks. The images are shown at double their original sizes. Since blocks are only 8 pixels wide, which is extremely difficult to see, the image is 200 pixel by 220 pixel original image, which means that image will be separated into 700 blocks. 200 220 will be almost 44,000. So 44,000 divided by 8 or 64, that is will be almost 700 blocks, which some padding added at the bottom of the images. Also remember that division of an image is only a logical division, but in figure 3 lines are used to add clarity, which might not be exactly the division, but for clarity has been designed here. But there will be 700 blocks. If you go through the calculation, might be less also, but try to go through that. In the phase 2 of this JPEG algorithm, it is the conversion to the frequency domain. We are converting whole data from the bit level or information level to the frequency domain. At this point, it is possible to skip directly to the quantization step. However, we can greatly assist that stage by converting the pixel information from the spatial domain. Spatial means we only have that that bit value. Okay, that is spatial in the domain to the frequency domain. Means if we go to frequency domain, then there is time is also associated with that domain, but in case of bit, there is no time is associated with. The conversion will make it easier for the quantization process to know which parts of the image are less important, and it will de-emphasize those areas in order to save space. So that is the main idea or purpose of this step, that after changing from the spatial domain to the frequency domain, we will see which part of that that frequency is more important or less important. If some part of that image is less important, then we will not give give more emphasis on those areas, and we will leave that or de-emphasize those areas in order to save the space. Currently, each block in the block each value in the block represent the intensity of one pixel, because we are changing each block represent the intensity of one pixel. So obviously each value in a block represents the intensity of one pixel. Remember, our example is grayscale image. After converting the block to the frequency domain, so after converting the block to the frequency domain, each value will be amplitude of a unique cosine function. Try to relate this to statement. The cosine function each have different frequencies. We can represent the block by multiplying the functions with their corresponding amplitude. So we can represent the block by multiplying the functions with their corresponding amplitude, and the function is here cosine function, and the cosine function where we are using the amplitude level, and the amplitude level is getting from the intensity value that is being in the block, or its value in the block, or its pixel of the block. Then after multiplying the function with the corresponding amplitude, then adding the results together. However, we keep the functions separate during JPEG compression so that we may remove the information that makes the smallest contribution to the image. So human vision has a drop off at higher frequencies, and de-emphasizing or even removing completely higher frequency data from an image will give an image that appears very different to a computer but looks very close to the original to a human. The quantization stage uses this effect to remove the high frequency informations. So that is also one very important point, that is in the quantization stage. Quantize means we try to sample out and fix the level with some informed bit or coded form, that amplitude level. The quantization stages use this fact to remove high frequency information, which results in a smaller representation of the image. There are many algorithms that convert spatial information to frequency domain. The most obvious, which is first Fourier transform. However, due to the fact that image information does not contain any imaginary components, there is an algorithm that is even faster than an FFT, or first Fourier transform, that is discrete cosine transform, which is derived from the first Fourier transform. However, it requires fewer multiplication than FFT, since it's work only with the real numbers. So FFT works with imaginary numbers, but we have only discrete values or discrete numbers. That is why we are going with the DCT transform, or direct discrete cosine transform. However, it requires fewer multiplication than FFT, since it works only with real numbers. Also, DCT produces fewer significant coefficient in its results, which leads to greater compressions. Finally, the DCT is made to work one-dimensional data. Image data is given in blocks of dimensions, but we may add another summing term to the DCT to make equation two-dimensional. So actually we are using DCT, and in case of DCT we need only one-dimensional data made to work on one-dimensional data, but in the image data is given the blocks of two dimensions, but we may add another summing up term to the DCT to make the equation two-dimensional. In other words, applying the one-dimensional DCT once in the x direction and again once in the y direction will give effectively two-dimensional discrete cosine transform. So you can see the scenario here. So the 2D discrete cosine transform equation given in figure 4, where Cx is equal to 1 by root 2 is if x is 0 and Cx equal to 1 for all other cases. Also f of xy is the 8-bit image value at the coordinates xy, and fub is the new entry in the frequency matrix. So here in this equation, this is the discrete cosine transform equation, where here you can see in the both direction x and y, to find the uv value in the frequency domain, we are using the x and y value of the image value, that is the image value, because that is two-dimensional image. Okay, so that is the value of x and y, and there is 0 to 7 means 8 pixels are there, and this is the equation, and both will be used in case of finite two-dimensional discrete cosine form. So before going to this third part, and also in some part of these things, because it will lead to more time, I'll start from this space in the next video, uh, because it will take some time to complete the whole thing about JPEG. Then after completing the JPEG, we'll go to MP3 and MP4 if time permits. Okay, so try to go through the content what I have discussed till now, but I will continue from this page in the next video. So till then, if you have any confusion, please let me know. We'll try to resolve that over Google Meet. Thank you.